Alright guys, welcome back. We're going to be solving another question from the chapter 4 of Engineering Mechanics by Meriam, and we have the device that is used to straighten both decking board just prior to final nailing to the joint. There is a lower bracket that is not shown at point O, which fixes part OA to a joist, so that the pivot may be considered fixed. So we have a fixed pivot at that point, and for a given force P exerted perpendicular to the handle ABC, so we have this force P in here, we need to determine the corresponding normal force N applied to the bent board near point B. So we're going to have a normal force on this bent board, and we can neglect the friction, so no horizontal component. And as always, we need to start with the free body diagram. We are in equilibrium. We can use our equilibrium equations. And what I'm going to do in here is that I'm going to draw the free body diagram for the member ABC. And basically, since we are looking for the normal force at point B, if we just do the moment about point A, counterclockwise positive, we're going to get rid of all the unknowns that we have at A. So we have a plane we can consider two component, AY, AX. Let's just show our X and Y axis here. But again, we are not interested in the reaction at point A. We're interested at the normal force at point B, which would be the normal force that is applying to this board. So this is going to be our normal force. One thing that we need to keep in mind is that we have a little 2 degrees angle in here. So basically the normal force that we have is the normal force to the bent board, but we have also our vertical line. I'm gonna show it with different color, yellow, maybe this line, that since we know this angle is 2 degrees, this angle is also 2 degrees. Just show it with different color. So this angle right here is going to be 2 degrees as well, because of the same trick that we talked about when we have two angles like that, where another angle is perpendicular to each side of that. So this one to this one, these two are the same. We're going to have the same thing in here. Basically, what we have in here is these two and these two, each side perpendicular to the other one. So these two angles are the same. So now that we figured that angle, the rest of this is not very complicated. We're gonna have the moment of the force P about point A, which is going to be a counterclockwise moment, so positive P times, we are interested in the distance from A to the line of action of the force P, which is basically the length of the member ABC, so 175 plus 500. And we're going to have the moment of the normal force. First of all, just going to clean up the figure, we can see better. So we can see that this normal force about A is going to be in this direction. So it's a clockwise moment, so negative n. And now this is the trickiest part of the question, where we need to find the vertical distance from A to the line of action of the normal force. So if you just continue the line of action, we're going to make a right triangle in here, which I'm going to highlight it in yellow. So this right triangle in here. And since we have the hypotenuse of this right triangle is 175 millimeter, as long as we can find this angle, sine of that angle is going to give us the distance that we are looking for. So how we're going to find that? It's pretty easy. We figured that we have a 2 degrees angle in here, and also from the question we know that uh, this member makes 15 degrees with our horizontal, so this angle in here is also 15 degrees. So if we want to find the sum of these two angles, we basically have 15 plus 2 degrees or 17 degrees. And there we go. Now we have the distance. It's going to be, so this is going to be our right triangle in here. I'm just going to show it a little bigger, 175. And since this angle is 17 degrees, that's going to be 175 sine of 17. So 175 sine of 17 degrees equals 0. Again, because we assume that we are in equilibrium. So sum of all moments about any point has to be 0. And same for our force equation. Sum of all forces in x equals 0. And same for the y. But we don't need these two equations. That's why I didn't write it at the first place. So now we can find our n. It's basically 675 divided by 175 sine of 17 degrees times p. I did not do any unit conversion because everything is based on millimeter. So converting these to meters, just need to divide it by 1,000, which basically doesn't make any difference in our equation. So let's see what we get. 675 divided by 175 sine of 17. So our n is going to be 13.2 p. And that's going to be the final answer for this question. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.